want to thank you all for coming to my talk today about Cook Your Own AI, delicious recipes. For those that do not know Cody yet, Cody is the Kotlin mascot and will help me today to explore Cook and what it's all about. Who am I? My name is Simon. I'm a developer advocate at JetBrains, and for the past decade, I've been working as a principal engineer using Kotlin on the server side. And I'm also an open source project maintainer, and the most well-known project is probably the ArrowKT project that I've been maintaining for close to 10 years now. So AI agents, I'm sure you've all heard a lot about them already, but let's very quickly review what they're all about. So at some point, we give some input to an agent, and the agent is, in the first case, just going to send that input or that request to the LLM. And the LLM is going to respond with either an assistant message, which will be the message that returns to the user, or a tool call. And when the agent or the LLM needs to execute a tool call, it does so in the environment, and it sends back the tool results to the agent, which might return it to the LLM and continue this loop of calling these tools in a loop. And this is what we call the agent strategy. So the agent strategy is what decides if you're going to continue looping or how we are going to progress in this process of looping these tool calls and continuously sending these requests to the LLM. And what we hope to integrate this with is your existing JVM applications, whether it's Java or Kotlin. We already have a lot of enterprise systems built, and we want to integrate in our existing systems on the JVM without having to rewrite any of our code or without having to use Python. We want to be on the JVM because that's where we like to be. And since the previous release of Koog, there is also support for a full Java API, which I will be showing today alongside some Kotlin code. So to build your first AI agent, you just use the AI agent builder, and we specify the LLM model or the default LLM model that we want to use, and we specify a prompt executor. And the prompt executor is a delegator that takes our LLM clients, and we can very easily configure the LLM clients, in this case OpenAI, Anthropic, Google, OpenRouter, Olama, but there's also support for many more providers, and it's very easy to integrate your own custom providers as well. And then we can use this executor to run our agents against many different providers and models. We can also set up some different things like the system prompt, the temperature. I want to briefly hold with the max iterations. I already mentioned agents will be looping, right? And we typically don't want this to happen infinitely, right? So setting max iterations is the simplest way of setting a limit when the agent needs to stop. And agents are typed, of course, because Java and Kotlin are typed languages, right? So our AI agent is also typed. And here we have a very simple agent, so it takes a string as the input, and it returns a string as the output. So we can call the agent like this. We pass a string into the run function, and we get a string as the result. And here our question, what is the weather in London? Well, sadly, it can never accurately be answered because the LLM has no idea of the current weather in London. So to do that, or to solve that problem, we give tools to the agent, and we do that by using a tool registry. And in the tool registry, we can register all different kinds of tools. And then now that we've given it weather tools, it can actually fetch the current weather information for London, and it can give us an accurate response. And this is what the same code looks like in Kotlin. So we leverage Kotlin named parameters instead of builders, and we have a small DSL for tool registry, but we'll see many more DSLs later. So what are these tools, right? Tools is what empowers our agent to do actual and interesting work. But like I said, we already have a lot of enterprise system built. We have already a lot of Java and maybe Kotlin code that we've already written. And we want to reuse that existing code and allow our agents to reuse our existing infrastructure. So here's a simple Kotlin function, and Koog out of the box supports suspension, right? So you can easily integrate it to any async framework that's out there on the JVM. We can add descriptions specifically for the LLM onto our functions, and we can also add descriptions to the parameters of our functions. And we have this order details return type, which in my case was a Java record that I wrote some time ago. And we can also add LLM descriptions to our Java records, and these can seamlessly work together. So to our existing code, you might have some Spring service like this, and it has some dependency, right? Because, well, my previous function already showed it, right? Most of our code, to be useful, it relies on dependency, so it needs to be able to participate in our existing infrastructure, right? So here we have an order service. And to make it available, to make this class available to Koog, we need to implement the toolset interface. And the toolset interface is a simple marker interface that tells Koog to scan all the functions in the class, and every function is annotated with the add tool annotation will be considered a tool for the agent, right? And this makes it very easy to allow existing services to become tools, but to only allow a specific function as tools and not all the functions in your existing classes. But there's kind of a problem here. This load order function takes a user ID. That's typically not what I want to expose to my agent, because in this case, the agent might hallucinate a user ID. It might try to read orders that are not mine. So I don't want to give my agent access to all orders, right? So it's good practice to still create a new class that explicitly exposes the functions. In this case, it wraps the existing order service, and we also inject the user ID. And this way we can make sure that if you expose a load order function to the agent, that it can only load orders for the user that is using the agent, right? So by injecting the user ID and hard coding it in the load order function of our order service, we now guarantee that it will only load orders that are of the user we want it to load. Right, so writing tools is pretty straightforward, right? What about the strategy? This is where all the heavy work is going to be done. Right, and I already mentioned it. I think the most or best known strategy is a very simple one where you take some input values, send it to the LLM. In the case that there is an assistant message, you finish. If there's a tool call, you execute the tool call and you start looping. And we can write that in a functional DSL like this, where we have a functional strategy and get access to the AI agent context, which gives you access to all the powers of Koog. You get the input string function. We send the request to the LLM, and at the end, we're going to return some content. But in the middle, we're going to be looping for as long as the responses that we are getting are tool calls, right? And to execute the tool call, you just execute it in the environment, and Koog takes care of that. So we call this function on the context, and then we send that tool result back to the LLM, right? And we're going to continue doing that until we eventually get an assistant message, and then we'll exit the loop and return that result. We can do exactly the same in Kotlin, but as you might notice, the context value disappeared from our lambda because that is now implicitly provided in the Kotlin DSL, right? So the Kotlin DSL can allow for a slightly nicer syntax in this way of working. But when we are working with a symbol graph, we very quickly hit a wall, right? How can we scale this graph, right? How we can improve this graph? How can we make certain steps in our graph more deterministic? How can we create larger workflows that, achieve the goal that we want? Maybe if we gave this 100 tools, it might not behave the same as it did with 10 tools. So let's try and split things up a little bit. And we're going to try and create a more complex graph that consists out of subgraphs, and it solves a problem that I think a lot of us are familiar with, right? So if we compare this to a coding agent, identifying the problem of the user could be like the planning phase. Solving the problem could be like the implementation phase. Verifying the solution is the review phase. And then when the review is not successful, we need to adjust the solution. And we can loop verifying or reviewing and adjusting until we get the desired outcome. And then when we get the desired outcome, we finish. Right? So let's try building this strategy using Koog. And we're going to do that by leveraging domain modeling, right? Because we see that LLMs really like structure rather than just some plain text. So if we can provide structured data that is inside of our domain or exists in our existing domain, we can help the agent understand this domain better. So in the first step, we are getting some string input from our user in our chat support, for example, and we are going to create a plan to solve this issue. And the output that this subgraph gives is the issue summary, which is a simple record type. And what is interesting about this in Koog is we are not using structured output of the LLM, but we're actually telling the LLM you need to gather all the information you need to supply this final value. Right? So the issue summary is an exit tool, is what it's called in Koog, and the LLM or the agent can only call the exit tool when it has gathered all the required information. Oh, and as you might have noticed, you can also use JSON properties, so you can use existing Jackson annotations to modify the JSON schema specifically for your agent. And we can do the same thing in Kotlin with data classes and Kotlin serialization. So how do we build this subgraph? In Java, we use a builder. We use an AI agent subgraph builder, and we have to specify the input and output types, in this case, string and issue summary. We specify which model we want this specific subgraph to use. And in this case, I'm using the same model as the default model we configured before. And we specify the task it needs to execute. And here, I'm giving a very simple prompt example, but you can build very complex prompts, which we will see later on. And interesting, we specify limited tools, right? So we are here saying that during this subgraph, you can only use the conversational tools and the read tools, right? So again, if we compare this to coding agents, this is like saying you can read my code base, you can ask and discuss with me, but you cannot modify any files, right? So here, we make sure that during this phase, the agent and the LLM can only investigate and communicate to us to ask clarifying questions. And here is how we do the exact same in Kotlin. So we use the DSL syntax. We specify the input and the output type as the type parameters. We again use named parameters to create the same subgraph. So in the next step, where we're going to fix the problem, we need different tools, right? And in this phase, I'm telling the subgraph, you cannot communicate with the user anymore. You can still read and investigate the orders, but you also need to now write and update whatever you're doing. And that's going to give us a solution. And again, this is a data type. So we are now going from issue summary to issue solution. So we're going from structured data to structured data. And building a subgraph for that is very easy. It's exactly the same as before. But what I want to amplify here is we are giving it different tools, right? So instead of the conversation tool, we now have the write tool. And we're also using a different model. And if you're familiar with LLMs, maybe a red flag is going off. Because how does the LLM deal with a history that contains tool calls of tools that are no longer available, right? Some LLMs cannot deal with this, so we need a workaround. So what happens during our first phase, we have some chat history, it could be user and assistant messages, and we have a conversation tool call and a read tool call. The problem now is in our second subgraph, this conversation tool is not available. So Koog rewrites the conversation tool calls into regular messages. And this allows the LLM to still see the history, but it's not going to trip over the fact that the tool is not available. It also adds a new tool call, which is the write tool call. I'll answer questions at the end. Thank you. So what happens if in the later subgraph, the conversation, the read, and the write tool are all available? Well, Koog is smart enough to reinstate the tool calls so that the LLM that has the correct tool available will still see this as tool calls in the history. And all of this is also configurable and customizable. But this is the default strategy that Koog offers out of the box. So now we need to go to some review or verification step, right? So I have different tools again. And interesting, the verify subgraph returns a critical result of the input type. So what does that look like? Well, we again have a simple subgraph, but we do not specify any output type. We use the with verification builder method, and that automatically sets the critical result as the output type. In Kotlin, this again looks almost the same. We have the subgraph with verification node. We give it the pass in the input type, and we pass in the desired tools and model. So now we have some branching in our graph, right? Because the critical result or verifying the solution can either be successful or not. In the case that it is successful, well, we finish. In the case that it is not successful, we need to adjust the solution. And then potentially we need to loop, we need to verify the adjusted solution, and potentially we loop again here. The adjust node is not very interesting. It's exactly the same as we've already been doing before, but for completion, I want to mention it anyway. Now we have all these subgraphs defined. We still need to connect them, right? We still need to make sure that the agent and the graph knows how to transition from one subgraph to the other. So here we have a graph strategy builder, and we need to specify for our entire graph, right, which was this one, that we have, first we have a string input type, and eventually we are going to finish with an issue solution. So in our graph definition, we start with the string input type, and we finish with the final result of the last subgraph. And connecting these sequenced subgraphs is quite easy. We just say we go from start to identifying the problem. When we have identified the problem, we are going to fix the problem. And when we fix the problem, we are going to verify the solution, right? So this is very straightforward. In the Kotlin DSL, you can do something like this, where we leverage Kotlin infix functions to basically provide pipeline functions to pipeline these subgraphs together. But for the complex part, how does this branching work? Oh, and also all of this that we've seen is all type checked, and this is actually why this piece is going to be very interesting. So we need to create a custom edge, right? Because we are going to do something with branching. We specify that we go from verifying the solution to adjusting the solution on the condition that the verification result was not successful. Right, so here we provide the condition for the branching in our subgraph. But there is a problem. Our verification subgraph returns critical results, and the input of our adjust step is the string feedback, right? And this does not type match. So at this point, we have a compilation error. Our program does not compile. So we need to specifically transform the output of the verify solution subgraph to match the input of the adjust subgraph. And this is the string value of the feedback. Doing the looping back from adjust to verify is a simple, straightforward connection. And then finally, the other branching is we need to specify, of course, the opposite case when things were successful. So we go from verifying solution to the final results on the condition that it was successful. But again, we have a type mismatch. So we have to specify that we want to extract this issue solution from the critical result so that we can satisfy the output type of our graph. And now we've effectively built this entire graph using subgraphs. And this is what it looks like in Kotlin. So we again get some nice infix syntax, and we say we are going to register an edge, and the edge goes from verify solution forwarding to node finish on the condition that it was successful with the input of the original value. So what about custom nodes, right? Because node or subgraph These are all things that live in our graph that are wired together, and a subgraph is actually a higher level node. Everything is a node underneath. And how can you build your own powerful nodes? Well, you create an AI agent node, you specify the input and the output type, and then you provide a custom action. And this custom action is what's going to be executed in the node. And this can be anything like a validation service or sending an email, reaching out to the user, anything important that you need to do in your workflow. And this context type here, again, is the type that gives you access to all the machinery of Koog, as we'll see in a bit. In Kotlin, again, this looks very, very similar. So you create a node with the input and output type, and then you do your logic inside. And again, there is no context value here because the context is implicit available in the DSL. So what about history? We have written a rather large graph. All the subgraphs internally are looping. We had this looping between verifying and adjusting. So it's very easy to build a very large history, very large message history, and this can be quite expensive, right? So we need to do something. Even worse, you can hit the context limit. So we need to do something to manage this history. And again, compressing history is just a node in your graph with an input type, which is piped to the output because we are modifying something inside of the agent. We are not actually transforming the type. But compressing history is very, very difficult. And if you've worked with coding agents, then you might have seen the compaction line. And when you see the compaction line, things might get a little bit fishy. So you need to be very careful how you deal with compression. And one of the most easy ways is just to compress the entire history. But this is also maybe the most dangerous one. Because let's imagine that we have a history of 200,000 tokens. We're sending this entire history of 200,000 tokens to the LLM. And basically, on a gamble or with luck, we're trying to ask the LLM to summarize the entire history and keep the important facts, right? So it can be very easy for the LLM to do something wrong and erase critical information from your history. So a technique that we've seen works slightly better is chunking this history into smaller pieces, and instead of sending the entire history at once to the LLM, you split the history into 20 equivalent pieces, and you send each individual piece to the LLM. So for 200,000 tokens, you would send 20 messages of 10,000 tokens asking them to compress that context. And that works slightly better, but it's still risky. But we found that JetBrains from experience, what works really well is when you are compressing history that you explicitly state to the LLM what are the important facts that it needs to remember, right? So this is something that is built out of the box for you, and you can ask the LLM to retrieve facts from the history, and then you can specify which are the important details that should never be forgotten. And we've seen that you can get 6 to 7% performance increase by doing things properly. What is also what I want to note is that we are working with domain, right? So here we're working with ISO solution. So depending on where in your graph you're compressing history, you might be working with a different domain model. And it is also important that in that specific place in your graph, you optimize history compression specifically for that part of your graph. Right? Because depending on when you might be compressing, you might need to remember different facts. And it's also quite easy to implement your own compression history strategies. But typically, you don't want an arbitrary place or a specific place in your graph to always compress history, right? So it's quite common that we want to attach a condition to this. And this is a condition that is quite common. So here we are saying, we are getting the LLM, which is the underlying machinery of Koog. We are reading the current session where we are executing from, and then we're checking the latest usage of the tokens. And in this case, we're saying only compress the history when you have used more than 100,000 tokens. And this is exactly what that looks like in Kotlin. So as you can see, it benefits a little bit from the Kotlin DSL powers. So things are a little more readable. And what I want to mention is when you create branching like this, you always need to make sure that you also cover the opposite case, right? It's just like don't write an if without the else. Typically, when you create some branching, you also want to cover the other case, right? So if you are not over the 100,000 token limit, then straight away go from fixing the problem to verifying the solution. And since a couple of versions, we've already had Spring support, but since the latest release, we also have Spring AI support. So what does Spring AI support mean? You can have Spring AI powering Koog instead of Koog powering everything. So if you have an existing Spring AI configuration where you, for example, set up OpenAI, Anthropic, and Google, this can now power your Koog application. So by setting up Spring AI, you can automatically inject the prompt executor from Koog, right? So the prompt executor is now delegating to the Spring AI infrastructure. And then we can use a multi-LLM prompt executor to say, hey, I want this prompt executor to work over all the models that I've configured, or you specify a specific qualifier saying, hey, I want a prompt executor specifically only for OpenAI, right? So in this case, we can communicate with OpenAI, Anthropic, and Google, because that's what we configured in Spring AI. And in this case, we can only communicate with OpenAI because this prompt executor is only connected to the OpenAI LLM client. So now that we've done all of that, we can call the create agent function with our prompt executor, which is the graph that we built in our previous section. And then you can run your agent, but more importantly, you can also specify user session. So what does these sessions do? Well, they relate to features, and features in Koog are installable or pluggable systems that you can plug into your agent, and you can then benefit from a lot of behavior. So let's review some of the features. Chat history or chat memory. So for those that have been working with agents for a long time, well, we typically or often we don't ask the agent one questions, but we might ask them several in a row, and chat memory guarantees that the history is persisted across agent calls, right? But only given the session ID, right? So how does this work? Again, this is being powered by Spring AI. So if you have DOM data source configured and you have Spring AI configured to use your GDBC repositories, then this chat history provider can automatically be wired for you, and we can now automatically just inject it into any of our services and just pass it to Koog. So what about persistence? And persistence is very different from chat memory. So we built a quite large agent, and there's people pushing agents to their limits, running them for 10 hours, 15 hours, maybe even more. But of course, things can crash, your pods can crash, your server can crash. And well, you have already paid a lot of money if it has been running for 10 hours or more. So you want something so that it can resume, right? And that's exactly what persistent does. And this is also where graphs start benefiting us more and more. So what is happening while we are progressing throughout our graph, every node that is completed gets persisted, and then when the agent crashes, you can resume from the last completed node, right? So this allows you to automatically resume from the last failure point. But since Spring AI does not have this concept of persistence, you need to manually provide a bean that provides persistent storage. Luckily, you can very easily do so with bypassing your data source and using GDBC. And it takes some optional parameters, which is the table name, the time to live, a migrator, and a JSON schema. The migrator and the JSON schema you probably never have to touch, but time to live might be an interesting one. By default, there is none, so it stays persisted forever. And well, maybe you don't want agent checkpoints as your table name. So yeah, it's probably a good idea to customize your table names. So what if I have both chat memory and persistence installed in my agent? How do they collaborate? How does it work? Well, first of all, everything is based on this user session ID. right? So without the user session ID, the user always considers this as a new run with no history. So if no session exists, it is always considered as a new chat. If a session was found, then the question is asked, did it complete successfully or not? In the case that it did not complete successfully, it will load the history from the chat memory, and it will resume from the last node that it was working on. But if it did complete successfully, we consider it as a new run, but the chat history or the chat memory is loaded, right? So that the agent knows all the communication that happened before. And with long running agents or with any long running program, you need to be able to figure out what's going on, right? So observability becomes very, very important with working with agents. Luckily, again, this is supported out of the box, and you can use it with any span exporter or span processor that you are already using today. But it also comes with specific support, for example, for observability platforms like Langfuse. And with Langfuse, you can just specify your API key, your project ID, and it will automatically export everything to Langfuse. And what is interesting about Langfuse is that it offers this graph-based view, right? And this will be the exact same graph that you created in Koog. And you can actually see a visual representation of your graph as it is running, and you can monitor what is it doing in the graph, what, why, and when. There's a couple of other popular platforms like Weave, which is also supported out of the box. And Weave does not offer this graph-based view, but it still offers you a very interesting view about which models were being used, what were the costs, what were the timings, and what actually went on in my agent. And here I'm again showing OpenTelemetry, but this is the Kotlin representation of the same configuration. So after the AI agent constructor, the constructor takes a lambda, which here is shown as a trailing lambda. In this trailing lambda, you have the feature DSL available, so you can install any feature, and inside of the feature installation lambda, you get access to the DSL to configure it. So here I'm configuring Datadog, and I'm using special syntax to initialize my trace attributes. And Datadog is a very popular framework, and it's in the recent time it started adding support for agent and LLM tools. So it gives us here specific information for Koog, for example, when the max iterations were exceeded. And it also gives you insights in latency, costs, token usage, and so on. So I hope that you learned something today here. But what I want to emphasize, Koog was built from our own needs within JetBrains to have a type-safe solution for building agents when we were originally using LangGraph with Python. And this type safety gives us the ability or the confidence to scale our agents. The plugins are very easy to write, and they are composable with all agents, and this allows for scalable architectures for writing plugins, sharing them with your teams, or open sourcing them and sharing them with everyone. Since the previous version we have full Java API support, and we are dedicated on providing good support in Java alongside Kotlin support, and we also have Spring support, which you can use with Spring AI or without Spring AI. So if you're not using Spring AI, you can have Koog power everything that we've seen today, but here today I showed Spring AI as the underlying engine. If you're not on the GVM, you can also still use Koog with Kotlin, since Kotlin and Koog are multi-platform ready, and they run anywhere: Linux, macOS, WebAssembly, JavaScript, Android, Apple, iOS, they run everywhere. There's so much more in Koog that I was not able to show you today. There's support for the ACP protocol, so you can also hook up your Koog agents in IntelliJ or Z. There's A2A, vector store support, RAG support, and so on. And finally, I think the GVM is an amazing platform for building your agentic services, whether you're using Koog or not. And I think OpenAI and Anthropic agree that Kotlin is also a great choice here, because both SDKs were 100% written in Kotlin. JetBrains also maintains the official Kotlin MCP and ACP SDK. And you can find all the examples I showed today in the Koog repository in the examples folder. You can also find a Gator example on my personal GitHub. I want to thank you all so much for coming, and if there's any questions, I'll gladly answer all of them.
Yeah, I had a question when you showed the fact that you use different tools for different engines, but you need to keep the history consistent. But there you are also switching from one model to the other, from, I don't remember the example, from ChatGPT to Anthropic. Does this mean that you have a first conversation with ChatGPT, you have the history, and then you use the same history with a different model?
Yes.
Does it work?
Yes, it works. Okay. So the only problem that we've seen is that if you take away one of the tools, and not all LLMs behave exactly the same, but some LLMs, if they do not have the tool available, but they see the tool call in the history, they crash, and they don't work. Okay. This is why we rewrite tool calls that are not available, and with that we see that this works perfectly across all providers. If you have any more questions about Koog or Kotlin, I'll be at the JetBrains booth the entire conference, so please come by and ask me any questions you might have. Thank you again.